Right, welcome back for the next part, which is also very important. The first part was more basics. I think you picked up on a couple of the basic concepts. The second part is mostly about being able to use your knowledge now and running into some calculations. So this is part 2, and I hope that after this part you will now be fine in terms of this topic. Alright, so let's go on. We now are going to look at Coulomb's law. Now, Coulomb's law is all about the force that two charged objects apply on one another. Now, we know that that force can either be in terms of repelling one another if they are having the similar charges on them, or it can be attraction if it is opposite charges there. So we know now that these electrostatic forces that acts on a body or on the two bodies is non-contact forces, and they act over a distance. And then Coulomb managed to state a law which bring all the variables together, and that law says that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Now there's a word here that you can easily overlook, and it's the proportional to the product of the magnitude of the charges. So we are looking here for the magnitude of the charges. We are not going to worry too much about the positive or the negative. It's the magnitude that's important. And here also then we're going to look at how far are they away from one another, the distance between them. Those are the two key things. So if we look at this equation, then this equation is basically Ohm's law in a symbol format, where you can see the force between the two objects is equal to the directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. So that is the second part. Alright, now looking at this formula, you will agree that this electrostatic force between the charges, be it now repelling or attraction, that they are, if there's an increase in the charges, if there's an increase in Q1 or Q2 or both of them, then we will have an increase in the electrostatic force. And also if there's an increase in the distance between the two charges, so if I increase this distance, so this number will be bigger, then we will find that the force will be decreasing, it will be smaller. That is inversely proportional there. Right, then important here is that the unit for Q must be in Coulomb, and also that the distance between the charges must be in meters, that R must be in meters, and then this Coulomb's constant K is given to you on your data sheet as 9 times 10 to the power 9. So it's easily to be found on your data sheet, it's given to you. Alright, so that's on your data sheet. Now we're going to look at some calculations. Let's say, for example, we have two charges. I've called it a charge E and a charge F, and we know that what is the magnitude of the charges, and I've given you that E is 4,8 times 10 to the power minus 16, and F is negative 2,2 times 10 to the power minus 16. So I've got my two charges, and then I show here that they are 1 meter apart. So you will agree I've got everything now. I've got Q1, I've got Q2, and I've got R. So it's a straightforward calculation to know what will be the force on F. So I know that there's going to be a force on F, there's going to be a force on E, and I want to know what will be the force on them. Let's take this before part first. I said here before and after touching. So we're first going to look at before they touch. They are just there, stationary, and now we know there's forces acting on them. So let's look at F. You will agree the one charge is negative, the other one is positive. there's my two charges. So I know that they will attract one another. So if I draw the free body diagram on F, then it will be a force to the left. It will be a force to the left. The force on E will be a force to the right, because they will attract one another. Easy calculation. I've got my formula. I substitute. Now here is the important thing, and that is that when we substitute now here, you will see that we don't substitute the negative 2,2, and the reason for that is we are looking for the magnitude of that charge only there. We know that the negative here of that 2,2, that negative only shows us is it repulsion or is it attraction. So we don't need it in calculating the magnitude of the force, and that's what this formula does. It gives us the magnitude of the electrostatic force. So that's why we can omit it, and we do omit it. We don't put it in there. And when we get our final answer, now knowing that it must be attraction, now I can just make a note saying, but this force will be to the left. And that, don't forget, because it is a vector. So at the end, after calculating the magnitude, you then will add saying what is also the direction. I hope this is quite clear, and this is a straightforward, easy calculation between two charged objects. Of course, if I tell you what is the force between the objects, and now I give you one of the two charges and the distance, you can easily calculate the other charge. That's also a possibility in terms of this calculation. Now let us look at what will happen now after they've touched. So that's the second part of the question, after they've touching. So this is now after touching. Alright, so the force on E will be, no, sorry, this was not already after touching. I just made a note here where I say the force on E will also be 9,5, the same as the force on F. It will just be to the right. I think that speaks for itself. And so what I've shown here is there's the force on E, there's the force on F. So the forces is equal to one another, but it's just opposite in direction from the negative. All right, so both the same magnitude, opposite in direction. All right, now I'm with the purple part, which is now after touching. All right, so here is my touching part. I'm letting them touch now. Now, if they touch, we know how to calculate the new charge on them, and I quickly did it here. I'm not going to waste time doing it again, but that is now the new charge on both of them. Now, that will now be substituted into Coulomb's law to calculate the magnitude of the force. So if I also now know that the charge on E and on F will be the same. So it's going to be the same charge. After touching, it's always the same charge, and it will always be repulsion. So that from there, it's 1,3 times 10 to the power minus 6 into both of them. So I just squared it there. All right, and it's still 1 meter apart, and I get an answer of 1.52 times 10 to the power minus 22. So now I know on F it will be repulsion, on E it will be repulsion. Same magnitude, both of them will experience a force, and now you can see the force is different from what the force between them was before they've touched, and it's correct because they have new charges on them. Same magnitude but opposite in direction, so that will still apply. Okay, but the force have changed. It looks like it is much less. It's about almost 5 times less, 5-6 times less than what it was now after they've touched. Okay, so that is when to show you some examples of using Coulomb's law. All right, now if I go on, I've got another type of question you can expect to get. It will be the type of question that deals with relationships. So let's just have a look here at one. I'm saying here that I've got a charge Q1 and a Q2, and I'm saying that there's a force of repulsion because they are both positive, and the magnitude of the force between them is F. So I also know that if that one is F, then this one will be F. Now the question here is, what will be the force if I double the charge on Q1 and on Q2? Now I'm showing you my way. There's lots of different ways of coming up with these type of questions where you are looking at relationships. So I'm not giving you values, but I'm showing you the relationship. So when I use Q1 and Q2 and R, then the force was F. That is what was given to me. Now I've doubled Q1 and I've doubled Q2. They are still R away from one another, so that didn't change. So what I did is I just multiply the 2 and the 2 with one another. It gives me a 4, and I wrote the 4 at the front. K Q1 Q2 over R squared is still equal to F. So then I get that the force will now be 4 times the original force. It will be 4F. So that is the type of questions that you can expect to get when you do relationship questions. Very nice multiple choice questions also, and it's popular questions to be asked. Okay, so another example now is if we go to three charges, and now we need to understand what happens here in terms of the forces that they apply on one another. Let us calculate the net force on charge E. So I want to know what is the net force on this charge. All right, now this charge is 1 meter away from F, so there will be an electrostatic force between E and F, and in this case it will be a force because of F, and it will be attraction. So the force on E because of F will be to the right, attraction between them. And now there's another charge which is G, and it's positive and positive, so the two of them will repel one another. So on E there will be a force because of G. That's just the way I like to write it, and that force will be to the left. When you draw a force diagram, make sure that you start from that dot. So this is the two forces direction that will be acting on E. Okay, so there I first found my direction. Now to get the magnitude is an easy question. The magnitude on E because of F, there I will add in the charge of E and the charge of F and the distance between them. So I'm going to use those two charges and the distance between them. But remember, you will see again the negative is out there because I'm only working with magnitude. So I get that answer. And then I know that one is the one that is to the right. So I've got this value, and it is that one there. Okay, now I can go and work out the other force that acts on charge E, and that will be between charge E and charge G according to my drawing. Alright, so it will be again only the positives. Both of them are in any case positive, so I just substituted there. And just look here, the two are now 2 meters apart, 1 meter plus 1 meter, so that's why I've got 2 meters square there, and I get my answer, and I've worked out its repulsion. So this one will be of that magnitude to the left. So now I have the force on E, which is to the left because of G. So I've got the magnitudes and I've got my directions. Now I have to make a choice to get F net, and I've chosen that to the right will be positive. Now F net is the effect of F of the two forces, so I add them together, but because of my direction, the one to the right will be positive, which was that one. The one to the left now will have to be negative because forces are vectors. And then I get my final answer, and because of the fact that this final answer is positive, I can say thus the net force direction is to the right because that was my positive direction. Alright, so I like to choose direction where I quickly look which one of the two are the largest value or the largest magnitude, and then I choose that direction as positive. It's going to sort out, then I know my answer most probably will be positive. It's little checkpoints that I use to check that I don't make mistakes. So there is an example of three forces, where three charges, where two forces will act on each one of them. So I could have gone and worked out what will be the net force on F, then I will look and say there will be attraction between those two. So there will be force on F to the left, and then there will be attraction between those two. So there will be a force to the right on F, and then I could work the two of them out, exactly what I did. And that you can go and do for each and every one of the charges to know what is the net force on each one of them. So this was where I calculated the F net on charge E. So you could have done it for all three of them, which you will normally in exam only get one to do. So that is on one dimension, on a straight line, my three forces. So now you will see there's also a possibility where we have three charges which is in 2D. In other words, they can also, in your syllabus, it will only be where the angle between them is a right angle, 90 degrees. All right, so I give you the values of the three, and I'm not going to do it right up to the answer. I just want to go through the process. I see there's a negative charge and a positive charge, and you will only be asked to work out the F net on the one which is on the right angle, so it will be G in this case. Okay, so there's my question. Calculate the F net on G. So I'm going to do two things. I'm going to look at direction as well as magnitude. Okay, so on G, first let's look at the direction. On G, there will be a force to the left because of E, which will be attraction because they are positive and negative. So that's what I draw there. The force because of E will be to the left. And that force I can calculate by using my normal Coulomb's law formula, where I will use E and G, the charges of them, and the 1 meter there. Okay, then I have the magnitude and the direction of E. Now the direction of the force between F and G will also be attraction. So what I have here is that on G it will be downwards, and thus I have that force, and I can calculate the force downwards using G and F. So that is what I will substitute in there, the charges, the 1 meter, and I will get that magnitude. So now I have these two magnitudes of those two forces. Now according to vector principles, if I have my two vectors tailed together, then this side will give me F net. So there is my F net. That one will be my F net. All right. Now, when I've got two vectors at a 90-degree angle with one another, then I can use Pythagoras, whereby I then will calculate what is the magnitude of F net using these two magnitudes. Okay, I hope that is clear. That is how so it's just something small that we add now when we are in 2D. But now let's get to direction. With direction now, we start from that axis and we work clockwise around up to F net to get the direction. Now I know that will then be 180 degrees plus theta. Okay, because theta is only that angle there. I've got the magnitude of FF, which is that force down. I've got the magnitude of FE, which is the one to the left, and there is my other angle of my triangle, and I may apply now trigonometry. So the tan of theta will be this side over this one. So there's many other possibilities. You could have used F net also. Okay, you might have said that the sine of theta is equal to Fe over F net. You will get the same value. All right, and then I calculate my theta from this, because I have those two. Either I could have used any one of the two, and now I just add my 180 degrees, which is that part there, and I have my direction. So I hope this, by saving a bit of time, you could see this is the only part that comes in. Those calculations is easy. So there's a bit of trigonometry when we go into 2D with our forces. All right. So that is an important part there. Good. Now if we go, that is the work in terms of, and calculations in terms of of Coulomb's law. Now we're going to go to electrical fields. All right, electrical fields is around any charged object. We say there is an electrical field, so we call that area around an object the electrical field. So that's why we will say, I said here, electrical field is a space or a region around an electrical charge, and that is where an electrical charge will now experience a force. That field will create a force that another charge will experience. All right, so this field, we can represent it in a diagram, and what we use for that is field lines. All right, now here is a couple of very, very important things when we draw the diagrams. All right, what do we want to see, and what do we conduct from our electrical field lines? First of all, we say the field lines are in the direction as indicated by the movement of a small positive test charge. So let's say I have a positive charge, like in my example here, then a small positive test charge will experience a force away from the positive charge, and that's why my direction is away. So this direction links to that rule. A small positive test charge will move away from a positive charge, or a small positive test charge will experience a force away, repulsion away from a positive test charge. And if we look at the negative one, now you will understand why the direction is towards the negative, because a small positive test charge will experience movement towards a negative charge, or you can say a force towards the negative, attraction force towards a negative charge. So that takes care of direction of my field lines. Right, the next thing is my field lines never cross, so you should not draw them where they cross. They should never cross one another. So that is also a property that you need to know. All right. Then also the area where field lines are close together. This is a very important one. That area where they are close together, that indicates a strong field. So you can see as I move away, the field lines are going further and further away from one another. Let us make an example. There, if I just extrapolate my field lines, you can see here they are much further away from one another than there when I'm closer to the charge. So here my electrical field is not as strong as what we have here, because the lines are closer together here. That is what is meant there with where the field lines are close together, it indicates a strong field, and where it's far away, it's a weak field. Okay, then the field lines begin and end at right angles, so it must leave that charge or that object at right angles. That's why we try and draw it so that it makes right angles with the charge. Right, and then our field lines is continuous. In other words, it goes on. It don't stop there where I choose to not draw it anymore. And then the last thing is, remember, this is three-dimensional. So we've drawn it here in 2 dimensions, but you must also realize there's going to be field lines coming out of the page and going into the page all around that sphere in 3 dimensions. So that is the properties of our electrical field lines. The most important ones that you must make sure that you are familiar with is the direction ones, and then also that you know where they are closer together, it indicates stronger electrical fields. The others is also important, because if you let them cross, you're going to lose a mark. If you don't begin on the surface, you're going to lose marks. If you don't do them perpendicular to the surface, then you're also going to lose marks. So let's add a number 7 here. Field lines start on the surface. No gaps. Be very accurate when you draw this. All right. Okay, so if we look at this one, then we can make the following 3 deductions from this. A small positive charge will be repelled. That's why the direction is away. The field around the single positive charge is not uniform as the field lines are not parallel. In other words, the field is not of the same strength as when the lines would be parallel. In this case, you can see the lines is going away from one another, further away, weaker field. All right, and that is also what they say at the third bullet, the field is stronger near to the positive charge. All right, so, and here we say now, there's a greater force on a small positive charge where the electrostatic field lines are closer together. So here is a way of calculating the electrical field strength. It is the force that the charge will experience. So a bigger force is when they are closer to that charge. So the bigger the force experienced by a test charge, the bigger will be my electrical field. Okay, the larger the force, the larger the electrical field. That is a directly proportionality. All right, so that is what we find there. And this charge is the test charge. It's not that charge in the drawing. It's a test charge that I put there. It's the force that that test charge is experiencing. And we know that where the field lines is closer together, that force must then be bigger because that will result in a bigger answer. The unit for electrical field strength is Newton per Coulomb. Newton per Coulomb. All right. Now there's the one for a negative charge, same pattern, just towards the negative, because a positive test charge will experience a force or movement towards the negative. So that is how we determine the direction of the field. We think about the positive test charge. Okay, now if this one at the top is negative Q, how will the field pattern look for negative 2Q? So then you can see there must be more field lines because it is a larger charge, which will result in now having field lines that is closer together. So at the same distance away, let's call it X, that electrical field strength will be more than at that same distance away that you will get from that one. The field lines is closer together. Okay. Stronger charge will give you stronger electrical field because of that charge. All right, and we will look at the way of calculating it now. All right, then you need to know these patterns out of your head when it's two charges opposite being charged, or two charges which is similar charges, positive, positive, negative, negative. All right, this is content that you need to study, you need to know them. All right, then now we want to calculate the electrical field strength. So we want to calculate E, that is the symbol we use for field strength. And I said at a point A, 0.5 meters away from this charge. And I gave you that charge, the Coulomb charge there, negative 2.4. So I want to know what is the electrical field strength at point A when it is 0.5 meters away. Now the formula that we use here to calculate this is this formula here, which is on your data sheet. All right, and you must be very careful when you look at this formula and when you look at the formula E equals FQ. This is where a charge is experiencing a force. So I will put a charge there at point A, and I will ask myself, what is the force that charge is experiencing there? So I'm going to use that charge that I put there, the value there, to substitute it, and the force that charge is experiencing there. But if I'm looking at, I just want to know what will be the field strength because of G, a certain distance away. Then I'm going to add in G there, and look again, the negative is omitted because I only want to get the magnitude of that electrical field. So this formula is going to give me the magnitude. All right, and I will substitute in the charge, I will substitute how far away from that charge, and I will get the electrical field strength. Now, how do I know the direction? The direction, I ask myself, in what direction will a positive test charge move. Now from here, a positive test charge will go to the left. So that's how I ended up with knowing that that electrical field at that point will be to the left. And it fits with what we've just done now, where we've said that is the electrical field around negative charge, and it will be towards. We've just now do that drawing, and now you will understand why it will be towards the negative there. Alright, so we use to determine the direction of the electrical field, we use the positive test charge way of doing it. Sorry for crossing that line, that I would have lost the mark there. It must stop and end, and it must start from the surface. So be accurate, don't be in a hurry like me and make mistakes where you might lose marks. Right, so that is one way of calculating the electrical field strength. Here I've got another example for you guys. Let's look at charge X. Charge X is 1,2 meters away from charge E. Okay, and I give you the value of charge E. I know it's a positive charge, and there's another charge that's 1.2 meters away. And I'm telling you that this charge E is experiencing this force. So we know, and that direction is given, it's away from X. So we know what is the force that X is going to experience. It will be in the opposite direction, but the same magnitude. We've done that now a couple of times. Yeah. Right, so there is my diagram to help me understand what's happening. I've got the charge E, which is positive. It was given to me as a positive, and I know what is the force. Now I can work out the direction of the force was given as away, so it will be to the left. So this is my free body diagram of the electrostatic forces on E. Alright, so now I want to calculate what is the electrical field strength here at E. Can you see? I know what is the force experienced by charge E. There it was given to me, the force experienced by charge E at this point. So now I'm going to use this formula. Right, so it's the force experienced by force E. And if I substitute that in, I get my magnitude. This will give me the magnitude. Now I have to decide on the direction. Now look carefully at this. I knew that this one is positive, and they told me that it experiences a force to the left. Then this one must also be positive. X must be positive. Right, X must be positive, because or else that force that this one experienced can't be to the left. Alright, so now I can ask myself, if I put a positive test charge here, where will it go? It will go away from this X, which is also positive, and that's how I determine the direction of that field with the positive test charge, knowing that it's going away. You can remember that the direction of the force and the direction of the electrical field will be in the same direction. Alright, so when you go and work through different scenarios, you will see that that is true. The direction of the electrical field here, because of X, will be in the same direction as the force that this charge is experiencing to the left. Okay, but I like to work it out with my situation of the positive test charge. Okay, I've calculated that one, I've determined it must be positive. That's the only way, and then I know that the positive test charge will go to the left. I hope this is quite clear when I use this formula and when I use this formula, the one there. Okay, so I hope that is quite clear. Right, then the last thing that we need to discuss is with electrical field strength is that it's possible to have three charges. Let's say I've got a charge here of 1 microcoulomb, which is 1 meter away from another charge which is 2 microcoulomb, which is 1 meter away from another charge which is 3 microcoulomb. Alright, and now I want to know what is the E net. What is the E net at the 1 microcoulomb. So I'm looking at what will be there's two electrical fields, one created by this charge, one created by this charge at that point. So that is what I want to know. I need to get those two electrical field strength. Okay, so now I can go and calculate the electrical field, the magnitude because of that 2 microcoulomb one. So let's call it number 2 will be equal to kq over r squared. And I'm going to substitute that charge that is creating the field 1 meter away. I could have drawn in the field lines going away from it, and I know that that electrical field will be to the left because this positive one, if I put a positive test charge here, it's going to move to the left. So I know that field strength will be to the left. Okay, so on that point, I know that electrical field 2, it's 2, will be to the left. Alright, now I can substitute here 9 times 10 to the power 9 multiplied by 2 times 10 to the power minus 6 over 1 squared, and I get an answer. And that will be to the left. Using what? Using my positive test charge agreement. Alright, now let's call that one charge 3, which will also have an electrical field around it. There will be lines going out from it to the outside, so I can calculate that one with this formula, q over r squared, and that will be 9 times 10 to the power 9 multiplied by 3 times 10 to the power minus 6 over, and now I see they are 2 meters apart, so it will be 2 squared. So I get that answer there, and now let's decide the direction. If that is a positive charge, then the field of this one will also be to the left. It will also be to the left. So now to get E net, I know it will be E2 plus E3, that's the 2 electrical fields that's in that space. And I'm going to choose my direction as left as positive because I've got 2 answers which is already to the left. So I will substitute those 2 answers. I will get my total, and that will also be to the left because both of them are to the left. I hope that helps you how to do electrical field strength, and guys, you will only get it in 1D. In other words, where the charges is on a straight line, not where they have a 90 degrees angle with one another. So yes, that is our topic. We've gone through everything. The last thing that I can look at to just have a final summary in terms of this work would be to say, let's just have a quick glance at graphs. Which graphs is applicable here? Now we have this formula, F equals KQ1 Q2 over R squared. From this, I know that F is directly proportional to the product of these two. That's in your definition. Okay, so my graph will look like this, directly proportional. Okay, and it will be the same if I only take Q1 or only take Q2. Same thing, it will be directly proportional. This means that if any one of those is larger, my answer will be larger, directly proportional. Now from this also we know that F is inversely proportional to the square of R. So this graph now follows. Where you get that curve, and you know that how can I make that a straight line? By using the reciprocal of that x-axis, which will then turn it around, and now I will have a straight line. Okay, and lastly, if we go to E equals KQ over r square, you will get the same kind of situation with E and Q being directly proportional and E and r squared being inversely proportional. And if we look at the other formula, E equals F over Q, then my E will be directly proportional to my F. So there is your graphs that you can expect to look at. Okay, which is coming directly from my formulas. Right, I hope part 1 and part 2 really will set you up now to be able to do the questions. Go to book 1. There's 15 papers of questions with answers, and you can really work through them, and I hope that this year we can do better in this section. Thank you so much.